Hello, this is Professor Nading, and in this particular section of Math 068, we're going to look at section 14, finding p-values. In the middle of this course, you'll find a little bit of discrepancy between section 14, 15, things like that in wording, but just go by simply the title and you'll be okay. We did some book changes mid-year, and they're all covered, but the numbers after about 14 got a little convoluted, so we'll do okay though. So in section 14. What we're talking about is using randomized distribution in Statkey. Statkey does a really great job of randomizing material for us. And when we're talking about Statkey in this particular function, we're talking about this right side over here. We're talking about the randomized hypothesis testing. So you've gone through the descriptive statistics, you've gone through the bootstrapping, now you're moving into the randomized hypothesis testing. It depends on if it's a single mean, a single proportion, a difference of means, difference of proportions. So first thing we want to make sure that we cover is all of the different determinations. So this type of variable that you're utilizing will be certainly dependent upon which area you're working in. So to have a discussion about here again, and we keep coming back to this over and over again, making sure that we have this. It's that important to us. And we have to make sure that within inside of these parameters and these sample statistics that we have the right information. Now I'm going to do a little bit of switching around. So I'm prepping a camera over here so I can actually see something just a little bit better for you. And in making these decisions on what we have and using these pieces or these different values, if you will. So let's talk that we have a single mean here. So in a single mean, remember that a single mean, the population parameter, talks about the population of the data. Got a sticky note under there. Population of the data. That's a mu value. Mean value of a single proportional parameter. Now, the sample statistic that goes along with that is always x bar. We're going to be testing an x bar value against a mu value. And you'll see what I mean when we get to the distribution. In a single proportion, that's a large p value, and p hat goes with that as a sample statistic. Difference in means is just two of these values. So it's a mu of a first minus a mu of a second. Likewise, it's an x bar of a first minus an x bar of a second. Remember, this is what we're testing. The difference in proportions will be these proportional values, but multiple values of them. And again, these p hat 1 minus p hat 2. And a correlation coefficient is always rho. Kind of looks like that. Or you can also use rho and a simple r value. Let me switch back over. And I'm also going to get rid of this right here. Don't need that. So when we talk about loading sample data into Statkey, and I think the best place for me to just do is just go to Statkey and calculate some of these and show you where they're at. So we're in Statkey. We can load a number of different things, and we've done this before. So let's say that I'm on single proportion, and inside of single proportion, I'm loading some kind of data. Remember, I can make the data changes over here if they've already been loaded for me. So I can go to the election poll support for Obama right here, and I can see that data. If I need to go out and get data, remember that I go to Statkey, I go to unlocking, I go to the actual data sets, and I grab the data set I want. I download it as a CSV, and I bring it back in. And you get back to Statkey here. Now, when I bring up some kind of randomized testing hypothesis, and I'm going to go to this mean one in just one second, you get these different data sets. And we got to remember is what happens in the different areas of that. So if I go to Statkey, and this time I'll go to single mean for test, I'll bring up the body temperature, which is the one that's at the very top. And the center value is the randomized dot plot for me running this with a mu value of 98.6. So the data that I produce will center itself on a nothing going on value of 98.26. However, the original sample data over here, these are the original 50 samples. It says n equal 50. And at the same time, it's got a mean of 98.26. The mu here does not match the mean here. Remember, this is the statistic. This is the population parameter as we create it. The standard error isn't available because we haven't produced anything yet. The randomized sample will be down here. Every time I pull another randomized sample, it will happen here. So if I do generate one sample, I get a mean value of 98.352 from these 50, and it plots it right here. That value is going to go right there. That's at 98.352. And the more number of times that I continue to do that, the more times it plots that data for me, and it continues to build around, again, the mu value of 98.6. So it says for quantitative data, you do an upload file. But for categorical data, we'll go in and we'll actually change the count and the sample size. For instance, back in here, Statkey. If I need to change a piece of data for a proportion, I just simply go in and I edit the data. When I edit the data, if I want, say, 3 out of, say, 17, so if 17 things were counted in my full count size, then 3/17 or 0.176 becomes my original sample statistic. You change randomized testing for proportions under edit data. And let me say okay. And let me go back to Statkey. Now, the mu, the null hypothesis. Remember, everything centers around the null itself. And in this case, the null is 98.6 with a mean. So what we want to do is we want to, if we need to, we can adjust the null hypothesis. So the null hypothesis at 98.6, if I were to change that, here's my single mean, and let me run some samples here. Let's run 1,000, and there they are right there. And my center is at 98.6. If for some reason I'm told to change the null hypothesis to, I don't know, 98.1, then I can change the null hypothesis, and then I can rerun my samples around that null hypothesis, and you can see here it is at 98.1. The null changes where the center of the randomized dot plot is taking place. So we would be testing a different null hypothesis at 98.1, if that were the case. And I'm going to go back just so we're back at the right place, 98.6. To randomize the distribution, we simply click on Generate a Sample, and I showed you this. This is the original sample, and the original sample has an original test statistic of 98.26. When it plots it, that is the mean of these 50 values that were taken. Now, when we go in and we take a test and we run a test here, every time it singularly runs a test here, it goes up into these 50, and remember, grabs them one by one and puts them back in 50 different times until it gets a mean. Then it takes that mean and it puts it over here in the randomized dot plot. And then it does it again. So if we had 1,000, it does that generating of 50 things 1,000 times, and it plots them in this curve. And remember where it centers it up at. It centers it up at around the null hypothesis. And the null hypothesis is always dead center in the middle of the curve. The standard error is developed up here in the top right. And we have our choice of testing hypotheses up here in the top left. So in order to test, we have to know what kind of tail we're talking about. Are we discussing things that are in a left tail? Are we discussing things in a right tail? Are we talking about things which are in a two-tail design? Well, that comes from the questions of the test or the test itself. If we have a left tail test, meaning we have something that we want to test a statistic for to see if it is less than, then the alternative hypothesis is a P1 less than P2. I'm testing to see if my proportion is less than some other proportional value. And that other proportional value is the null. In a right tail test, the tail will always be on the right side where the p-values exist. And the p-values will be tested because I'm looking to see if my randomized proportion right here is greater than some other value. I want to see if more than 40% of shoppers use coupons. And if I'm in a two-tail test, I don't care about being less. I don't care about being greater. I just care about being different. Remember, this is where we use the word differs from. In here, the H of A is P1 does not equal P2. And you can't see this side, but the p-value here is twice because on the next page, you'll see it's over here too. A two-tailed test considers this side and this side to be part of It's p-value. So when we test p-values for two-tailed test, it'll be the statistic times 2. And I'm going to type that. It's going to be 2 times the p-value of one side. Because it allows for the p-value to take place less, or to allow the p-value to take place here. Now notice all p-values on this side will be positive because they're on the right side, and all p-values will be negative because they're on this side. But in fact, they come together to make one double p-value. In student exercise number 1, it would like us to look at the null and the alternative hypothesis for the given test. Indicate whether the test is a left tail test, a right tail test, or a two-tail test. So in letter A, right here, H of O is P at 0.7. So my center of my distribution will be at 0.7. That's what I'm going to center up on right there. However, when I test, I'm testing to see if it's greater than. A greater than test is definitely a right tail test. When I look at the next one, B, the mu is centered up exactly at 10. The center of this curve will be at 10, and I'm testing to see if it's less than mu, or less than 10. So therefore, I would have a left tail test. Anytime a situation is a not equal, the centering of that statistical test is 0. My center will happen at 0. Remember, if I did a little algebra here, mu1 minus mu2 would equal 0. And that's how I know it centers itself at 0. And that's an important concept to know. It's a not equal test, and since it's a not equal test, it's a two-tail test. Not a left, it's not a right, it's a left and a right simultaneously. And in the last one, P1 equal to P2. Again, this one will be centered at 0. Oops. Centered at 0. However, it will be a right tail test because it's a greater than test. So if I show you that in Statkey, so if I were, first of all, I'll go back and I'll show you that 0 proportion. If I take the difference in two proportions, and I just run this test right here, it doesn't matter what it is, 1,000, you can see the null is 0. Why is the null 0? Because when you take P1 and you subtract P2, you get 0. If P1 equals P2, then P1 minus P2 equals 0. I can do that for you real quick. We've done this before. If P1 is equal to P2 in my H sub O, then as I subtract P2 from both sides, then P1 minus P2 equals 0. And that's why the null hypothesis is centered up at 0 on a subtraction of either proportions or means, either one. So this test statistic, this thing that we're looking at, so for instance, in this body temperature one, we are looking to test the body temperature on the mu of 98.6, but we want to use this sample over here to test. Well, what you notice over here is this sample is 98.26. It's up in the top right-hand corner. Circle that for you, right here. You find the original test statistic data right here. Okay, so what are we going to do? We are going to take this run of randomized mean for body temperature. So we're going to go here. We're going to go to single mean. And this is just an example. We're in body temperature. I'm going to run 1,000 of these. I'm also going to run it. And if you notice, this is a two-tail test. See, it's got a left side p-value and a right side p-value. How come? Because remember, we were testing to see not equal to. We didn't care about greater. We didn't care about less. Right now, we just cared about not equal to. So when I run my two-tail test right here, you can notice I get numbers right here. I get cutoffs down at the bottom and down the bottom. Well, this bottom is 98.4, but my statistic is 98.26. So first of all, 98.26 is on the left side of the null hypothesis. You would never try to put 98.26 over here. If this was 98.9, then I would test over here because 98.9 is on the right side of the null. I'm going to take this 98.26, I'm going to put it right here. I'm going to click on the box, and I'm going to change it to 98.26. I'm going to hit enter. You can see that my p-value, because of this, my p-value just changed itself right here to 0.001. 0.001. But remember, there's a 0.001 here, and remember, not equal includes the other side, the right side. So there's another 0.001 over here. So when I calculate my statistical value for my t-test, or for my p-value right here, then I'm going to have to make sure that I include 2 times the value of 0.001 or 0.002. This is my p-value right here. The proportion of times, or the rareness and rare instance of when this happens, is all the way down to a significance of 0.002. It's incredibly rare for this to happen because that p-value is so very, very small. Student exercise number 2. It says the null hypothesis as well as the sample are given. It has some sample data there, and it asks us to identify, first of all, the sample statistics. So let me find a piece of paper I can write on for you, and we'll do these. So first of all, we have an H sub O, and I'm just going to switch over to my camera because it's going to be easier for me to discuss and write right here. So we have first of all, we have a null hypothesis at P1 equal P2. So I want to remind you that that means the null hypothesis is centered at 0. The H sub A says this is a two-tailed test. So I'm going to write that down too. It's a two-tailed. How do I know it's a two-tail? It's a not equal. Not all not equals are in that form of two-tail. The first sample data is 24 over 30, or 0.8, and the second sample data, P2, p hat 2, is 14 out of 20, or 0.7. Identify the statistic using appropriate notation. Well, the appropriate data is that when I look at p hat 1 and p hat 2, I'm going to take p hat 1 and I'm going to subtract p hat 2. Well, p hat 1 is 0.8. P hat 2 is 0.7. And when I subtract those two, it's 0.1. This is my appropriate test statistic. 0.1. So I am in fact testing 0.1. I am not testing 0.8. I am not testing 0.7. I'm testing everything that has to do with 0.1 because that's the difference of these two. List the steps necessary to find the p-value. Okay, so we're just going to walk through those and then you can come back and fill those in. So what would I do as far as step number 1 goes? Well, step number 1 is I have to actually click on the difference in proportions. So that would be my first step. My second step would be to edit the data because this data is not coming from here. It's coming from a question that they gave me. Then my next thing is to fill in the count values here. Well, the first count value was 24 out of 30. That was for proportion number 1. Proportion number 2 was 14 out of 20. And I got to hit go there. So we are down in through already. We just did this sample sizing right here. So the next thing is, okay, what am I going to do now? Well, first of all, I want to look at my test statistic, and then we're going to run it so we can see some samples. So what do we got to do? You don't see anything in the middle. Well, why don't I see anything in the middle? Because I haven't run anything yet. First of all, let's check over here. Group 1, 0.8, group 2, 0.7, group 1 minus group 2. Notice it automatically subtracted the 2 for the same statistic I came up with, which was 0.1. I'm going to generate 1,000 samples right away. Boom, there they are. Now, the question is, okay, what kind of test do I want to run here? Okay, so if I go back to this particular test, remember in the original hypothesis testing, the H sub A was P1 does not equal P2. So that automatically tells me it's a two-tailed test. So right now I have a two-tailed design. Oops. I have a two-tailed test going on right here. I'm going to get rid of that box, get it out of our way. Now what? Okay, well, my next step would be, okay, my test statistic is 0.1, and I need to test that. So look at the left side data over here. These are test statistics on the bottom. They're just randomly produced. They're not the ones we want, but they're just randomly produced on a 95% CI. These are the negative test statistics. These are the positive test statistics. I have a positive test statistic. I'm going to change this test statistic to 0.1 because that's what we tested at. Notice when I tested 0.1, I get 0.310 on one side. That indicates to me that I'm going to have 2 times 0.31 for my test, for my p-value. So when I get down to here, this test statistic actually had 0.267, and they changed it. And then you can see, look at that, 331. So we are exactly where we were at 310. And remember, there's always a slight difference. We have 310, they have 331, and that will happen over and over again. So the question says right here, what's the p-value for this hypothesis test? Well, this one would be 2 times 0.331. The one I just ran would be 2 times 0.310. I'll go with what's sitting right here because that's what's in your notes. P-value equals, now remember, it would be whatever you ran on your machine at the given time. And we know, everybody knows, that there is going to be a slight difference in that value. And 331, that's going to be 662. Not very significant. Large p-values don't mean anything. It's small p-values that come into count and matter for us. And that is section 14. When you come to section 15, remember I told you that the labeling may be off a little bit. Just simply look for the label of sketching area under a normal curve, and everything in life will be awesome.